Hi everybody, this is Mostapha Kalami from Yarpiz, and I'm going to teach you what is particle swarm optimization, or in short PSO, and how to implement PSO using MATLAB programming language. Firstly, we will review the theoretical foundations of particle swarm optimization, and we'll see how PSO works and how it solves optimization problems. Then, based on these theoretical foundations, we will implement PSO in MATLAB from scratch, describing every line of code. This enables you to know how PSO works and how to implement PSO to solve your own optimization problems and any kind of problem that can be stated as an optimization task. Okay, let's start with the video tutorial of particle swarm optimization in MATLAB. Particle swarm optimization, or PSO, is an intelligent optimization algorithm. It belongs to a class of optimization algorithms called meta-heuristics. PSO is based on the paradigm of swarm intelligence, and it is inspired by social behavior of animals like fish and birds. PSO is a simple yet powerful optimization algorithm, and it is successfully applied to enormous applications in various fields of science and engineering like machine learning, image processing, data mining, operational research, and many other fields. Initially, PSO is introduced by James Kennedy and Russell C. Eberhart in 1995. Originally, they were working to develop a model to describe the social behavior of animals like flock of birds and a school of fish. However, they realized that their model is capable of doing optimization tasks. So they proposed a new optimizer based on their model, which is called particle swarm optimization. An image of their original paper is shown here, which is entitled A New Optimizer Using Particle Swarm Theory. In the last 20 years, since 1995, the introduction of PSO became one of the most useful and most popular algorithms to solve various optimization problems in various fields. One of the key points behind the PSO is its simplicity. PSO is a very simple algorithm. However, it is a powerful algorithm too. Let's start with a simple example to show how PSO works. Let's assume a slice of a lake or a one-dimensional fictional lake. This is the shape of the lake, and this is the surface of the water. Assume Alice and Bob are two friends, and they are looking for the deepest location in this lake. They would like to cooperate to solve this problem. Obviously, this is a search problem and can be stated as an optimization problem too. Alice and Bob have two boats and have measurement tools to measure the depths of the lake at every location. At the first, the boat of Alice stays here, and the boat for Bob stays here. They both measure the depths, and they inform the measured depths to each other. In this situation, the depth measured by Alice is greater. So Bob moves a step towards Alice and updates his location and makes another measurement. This measurement is deeper than the last measurement made by Alice. So Alice moves towards Bob a small step, and she also makes another measurement. But in this situation, Bob still is on a deeper location. So Alice moves another step and makes another measurement, another movement, and another measurement to reach this location. And obviously, this is the global minimum of this problem. Global minimum of this problem is obviously here. But Alice and Bob don't know the answer. They should cooperate to find this answer. Alice is now on the global minimum, but Bob continues to move towards Alice. And movements of Bob are shown here. Another movement. And finally, Alice and Bob meet each other in this location. So they find answer for this optimization problem. PSO is very similar to the search mechanism that Alice and Bob used. In the structure of this cooperation, two principles are used. These two principles are communication, which is informing the measured depths to the other party, plus learning. When Alice moves towards Bob or Bob moves towards Alice, they actually learn that location of the other party is better. Learning the concept of better is the main problem that an optimizer should solve. When an optimizer learns the concept of better, it is able to solve any kind of optimization problem. Because the solution of optimization problem is to find the best one. So if we know what is the better, we actually can discover the concept of best. In this simple story, the cooperation of Alice and Bob to find the global minimum of a one-dimensional function, we simply discussed about the basic rules behind the swarm intelligence. Alice and Bob don't know about the global minimum of the problem. However, via cooperation, they are able to find the answer. And the swarm intelligence is something very similar to this. In swarm intelligence, an intelligent behavior is created by means of some agents, like birds, like ants, like fish. And this level of intelligence is absolutely unreachable for any member of the swarm. But with cooperation among the members of swarm, among the members of colony, this level of intelligence can be reached. And this is the concept, the paradigm of swarm intelligence. PSO is a swarm intelligence method, and it uses some unintelligent agents called particles to reach an upper level of intelligence, which is absolutely unreachable for any of particles in the swarm. Okay, let's see how particle swarm optimization works. Particle swarm optimization contains a population of candidate solutions called a swarm. So we have a swarm of candidate solutions called particles in PSO. Every particle is a candidate solution to the optimization problem we are going to solve it. Any particle has a position in the search space of the optimization problem. The search space is the set of all possible solutions to the optimization problem. And we would like to find the best solution among these solutions, these possible solutions in the search space. For particle I, the position of particle is denoted by xi. This is a vector, and it is a member of search space, denoted by x. To distinguish between time steps, we add a time index to this position 2 and denote it by t. It's a discrete time step, and it shows the iteration number of the algorithm. The I is the index of particle, and x is the vector of position. For example, in the example of Alice and Bob, the position is a value between 0 and 1, for example. And the search space is the set of all real numbers from 0 to 1. And on each time step, the position of Alice and Bob is a real valued number between 0 and 1. And because the search space is one-dimensional, it's a scalar. The position of Alice in the beginning of algorithm is denoted by x Alice in the beginning of algorithm. And this is the position of Bob in the beginning of algorithm, and so forth. So we denote the position of particle I in time step t by xit. This is a vector. In addition to the position, we have a velocity for every particle, which is denoted by vit. This is a vector too, and it is in the same space as the position. The dimensions of v and x are same. The velocity describes the movement of particle I in the sense of direction and in the sense of distance and the step size. So we have a particle, in time step t, which is located in the position xit, and it moves towards a vector like vit. This is a particle, a simple model of moving particle. But this particle is not alone. It is a member of a swarm, and just like the example of Alice and Bob, particles are interacting, are learning from each other, obeying some simple rules to find the best solution for an optimization problem. By defining the mathematical model of motion of particles in the particle swarm optimization, we will get an optimization tool to solve the optimization problems. In addition to position and velocity, every particle has a memory of its own best position, best experience. This is denoted by personal best, and I'm going to draw it as PIT. This is a position 2, and this is the best experience of the particle I. In addition to this personal best, we have a common best experience among the members of swarm, denoted by GT. Note that this has not an index of I because it belongs to whole swarm, and it is not a particle-specific experience. It's a common and swarm experience. It's a global best and global common experience among the members of swarm. So we have a personal best for every particle, and we have a global best, which is the best experience of all particles in the swarm. The mathematical model of PSO is very, very simple. By defining these concepts, on every iteration of PSO, position and velocity of every particle is updated according to this simple mechanism. Let's define a vector from current position to personal best. This is the vector from x to p, and a vector which connects current position to the global best. If we'd like to write down the equation for this vector, it is obviously the end point minus the beginning point. So PIT minus XIT is this vector, and for this one is the GT minus XIT. The particle moves toward a new position, but uses all these vectors, all these three components. The particle moves somewhat parallel to this vector, to the vector of velocity, and somewhat parallel to the vector connecting xi to pi, and moves somewhat parallel to the vector connecting xi to global best. And this is the new updated position, denoted by xit plus 1. It's the new position. And the addition of these three vectors from the beginning of first vector to the end of third vector is its new velocity, vit plus 1. This is the simple model behind PSO, and the new position is created according to the previous velocity, to personal best, and to the global best. So this is probably a better location because it uses the previous decision about the movement of this particle, and it uses the previous experience of the particle itself, and it uses the previous experience of whole swarm. So this is probably a better location. Based on this simple model and obeying these rules by every particle in the swarm, Hopefully, the particles will cooperate to find the best location in the search space, the best solution possible for the optimization problem. The mathematical model of motion of particles in the PSO can be described as follows. One of the equations, which is simpler, is the equation for updating the position of particles, and it can be described as xit plus 1 equals to xit plus vit plus 1. And I'm removing the vector symbols for simplicity. This is the equation for updating the position. However, vit plus 1 has its own update equation. vit plus 1 equals to sum of three components parallel to previous velocity, parallel to the vector connecting xi to pi, and parallel to the vector connecting xi to gt. For the first component, we denote it as w, it is a real valued coefficient, w times vit, plus a real valued coefficient, c1, times this vector, pit minus xit, plus c2 times gt minus xit. And these two equations completely describe the mathematical model of PSO. However, these equations are simplified versions of mathematical model behind the standard PSO, and some considerations are necessary to complete the equations. The standard PSO is as follows. The equation for updating the velocity of particles is as follows. Vij in time step t plus 1. This denotes the velocity of particle I in time step t plus 1 and the j's component of this velocity. And this is a scalar value. Vij t plus 1 equals to w Vij in time step t plus a random number uniformly distributed in the range of 0 to 1, r1, times c1, a coefficient known as acceleration coefficient, times pijt minus xijt, and by j, it's obviously we are considering the j's component, plus r2, this is also as r1, a uniformly distributed random number in the range of 0 to 1, r2, c2, also this is another acceleration coefficient, gjt, the j's component of global best at time step t, minus xijt. And we know that r1 and r2 are uniformly distributed numbers in the range of 0 to 1. This is the equation for updating the velocity of particle I in time step t. And the equation for updating the position is same, or it can be stated as the component-wise version, like xij t plus 1 equals to xij t plus vij t plus 1. These two equations are two simple rules, which are guaranteed to obey by all of particles in the swarm. And this is the concept of swarm intelligence behind the PSO. As you see, this is a very simple mathematical model. However, this is a very powerful tool to solve various kinds of optimization problems. Let's investigate the components of these equations. This term is the inertia term, and the W, the coefficient W, is the inertia coefficient. In the original version of PSO proposed in 1995, there were not any inertia term. However, in 1998, Eberhardt and Shi added this term to the model of standard PSO. These coefficients, C1 and C2, are acceleration coefficients, and this term, known as the cognitive component, and this term is known as social component. And we combine these three components to create a new velocity vector. And this new velocity vector translates the position to a new position in the search space. And according to this model, this geometrical representation of the PSO, this new location is probably a better location for the particle I. Now we know how PSO works and how particles are cooperating to find the best solution for an optimization problem. This is a very simple model and can be implemented by any programming language. However, in this video tutorial, for its simplicity, we selected MATLAB programming language. And in the following sections of this video tutorial, we are going to implement the PSO from scratch and line by line, describing every line of code.